Good to hear you.
Hi.
Okay, so we're going to start. So today we are basically starting with the basic ingredients we need for forming a linear system and eventually solving one with any dimension, but potentially very large scale systems. So we're going to talk about vectors, matrices, and determinants. But we will only talk about determinants as a tool. It has a very deep geometric meaning. It's a very challenging topic, typically in linear algebra, to the point that some people believe we shouldn't teach it. So there are books that leave determinants out from the whole book. But it's very useful in practice, and it has beautiful meanings too. As we make progress, we can always get back or discuss on Piazza and give it better meaning. But think about it from the utility perspective. It's a tool. It can evaluate something uniquely, and we can check the system that we built, whether it's solvable or not. So because of that, it is still useful from the applied point of view. Okay. So we want to understand the vocabulary, some technical terms. So when we communicate, we understand each other better. These are the standard terms usually, although there might not be sometimes unique term for one particular thing that we call, but typically we use the standard terms. And we want to learn the difference between scalars, arrays, vectors, row vectors, column vectors, what's a rectangular matrix, what's the square matrix, what's diagonal, and eventually the determinant of a square matrix. And hopefully, when you walk out of this lecture, if you've never seen it before, it's not something that you necessarily need to practice. It's just when it's explained, when you look at it, then you understand what it means. So let's start with the scalars. Scalars are numbers that you've been using for a very long time. So any number like this, in general, you can call it a scalar. So the number can be negative, positive, square root, pi. This is famous pi number. As an engineer, I only know the 4 first digits, so that's enough for us to solve problems. But it continues, obviously. And you can see that now I'm defining these scalars in Julia. And you're welcome to type it now or later, try for yourself. You can define your numbers. Jesse told you yesterday, this is a float number because you have this floating point here. So before floating point, you have the integer. After that, you have the decimal points. And typically, we have single precision and double precision in the machine. Single, 16 numbers you keep after the dot. Double, you keep 32. Although you can have double that has 64 as well. That depends on the CPU architecture as well. Square root, it's defined in Julia. You can use it. One nice thing about Julia is that you can type your Greek letter into the code. Usually type the letter name and then use tab. It will convert it for you. Now, what does it mean to use this equality sign? Now, we know what it means on paper, but in a program, this means a sign, right? When I say A equals 25.77763, it means assign the right-hand side to the left-hand side variable. That's what the computer is understood. Print line, I'm printing whatever text you see, hello scalars, followed by new line. If you're familiar with C, you have \n, you tell the computer go to the next line. Print ln, print line, it will do it for you automatically. If you don't use that, you can use print, it won't go to the next line. So you might just print with continuing your variables. Just some Julia tips you can practice. And I think you could move this quotation here into the end and use a $sign. Try that. I think it works. So $sign, because it's inside the quotation, it's a string. It's just a text. That's what the computer understands. But when you use $sign, it means that go get the value of this variable that is attached to the $sign. This is a syntax that you ever worked with Linux or Unix machine. That's also very common. But in any case, it's not super important. You can practice this thing in the lab, or you can post it on Piazza if you find it strange. So these are the scalars. We are interested more in arrays. Arrays are basically a group of scalars organized somehow into a list. So a list of scalars can form an array of numbers. Now, array, you can have array of objects, of course. You can have car, airplane, coffee mug. But we're talking about numbers here. So arrays are just a list of scalars. So arrays can be rectangular or not. They can be in a column or row. If you ever worked with spreadsheet, you know what's an array. You open the application and you see a screen and you have rows and columns you can type in. You get an array of whatever you type. And in computer programming languages, usually you might come across as something that's called array as well. Maybe it can be used as a vector as well, but maybe you have a vector type, array type. Array tends to be more general than vector. In any case, arrays are for us just lists of numbers. I want to define a row array here. It is 1 by 5. And I can use equality sign to do that. In Julia, you open a bracket, and I'm typing 1 minus 2, 4, 8.1, and pi. So we try this, and we learn that if the syntax is that if you use a space, it creates a row array. Now, if you use comma, it will turn it into a column. Now it's a 5 by 1, 5 element. Okay? That's just by definition, that's the syntax. Or you can use semicolon. So the comma and semicolon are the same, whichever you prefer. So they are not the same, although you might have some functions that the function doesn't care if it's a row or a column, because it wants to just take each number and do something. But sometimes, especially in linear algebra routines, when we want to do multiplication between vectors and matrices, it is very important. We will learn later that the dimensionality is important when we arrange it in a row or a column. Okay. Now, we use comma and semicolon to define B and C. But I use exactly the same entries. Is there a way we check whether they're equal or not? There is. You can use this double equality sign. So this is very different from single one. Single equality sign was for assigning, right? The right-hand side to the left-hand side name, the variable name. When you use double equality sign, it checks if this statement, if left and right are equal. And the output is a logical outcome. Is it true or false? So it's a binary 0, 1, true, false. In this case, it's true. Which, by the way, we just learned that two arrays are equal if what? We never learned a formal statement about that. We just use the computer program, and we want to conclude that that must be the case. And it is the case. So what is the condition to say B and C are equal?
If they have the same values at the specific index?
Exactly. That's right. So if they have exactly the same value for each of their integers, then we say they're equal.
So, but what about A? It has the same value for each index, but it's a little, would it be not equal to B or C?
That's a very interesting question. Now, I don't think they are now, they are in the sense that we can see it's the same vector, but in the sense that it's a row vector and the other one is a column vector, they are not the same. Now, you can try this in Julia and maybe post it on Piazza and let us know. I'm working with a passive screen here. Or it's a good thing to try in the lab or on your computer. Check and see. It's a very interesting question. Is A equal B or C? Because one of them is row vector, one of them is column. I think it's not. Who knows? Maybe creators of Julia decided to say it is. But I think it's not. Because there's a dimensionality mismatch here. However, sometimes the program might surpass that to say, well, it's understood that these are just vectors. I'm going to ignore that this is a row, this is a column. But strictly speaking, in math, they're not, right? That's what I mean. Let's see what we have in chat. Trippy says dimensions matter. So I think what I said was right. Yeah?
So in Julia, can you form 2D arrays?
Yeah, that's what we're going to do.
Then how does, I'm basing this off of MATLAB experience, but commas usually still denote row arrays in MATLAB, and semicolons denote columns.
Okay, so I need to repeat the question because you shouldn't feel bad when I repeat the question. I'm not questioning your intelligence because I need to repeat it for the Zoom, right? So the question is, can we define multidimensional array except vector? And what is the relationship between the syntax we use in Julia with other programs like MATLAB? Because we can use column and semicolon as well. Now, if you never use MATLAB, you don't have that question. If you used it, you might find it surprising. Okay? Now, the first question, we can define multi-dimensional array, and we will do it soon. That's called a matrix. About MATLAB, in MATLAB, it's called MATLAB, Matrix Laboratory. That was the program started to replace Fortran or make it easier. Fortran was the initial scientific programming language, very old time. If you see a very, very senior professor, probably that professor can code in Fortran. That's the rule of thumb. Somebody around my age, or Jesse, they can code in MATLAB. We could pick up Julia quickly because it's very similar. Julia is more modern. They invent a new program, try to fix whatever was wrong with the previous ones. That's the idea. So in MATLAB, space will do the same thing. However, comma will be similar to space. In Julia, comma is similar to semicolon. And semicolon is the same in MATLAB and Julia. It goes to the next line. So when you can read it like this: 1, semicolon, go to the next line, right? -2, semicolon, go to the next line. So you go to the next line, semicolon, go to the next line, next line. Now, when you use comma in Julia, it does the same thing, but in MATLAB, it won't. It will create a row vector. So, comma is different. In Julia and MATLAB. And Trip is saying semicolon is next line always. We can make that a statement. Even if you code in C++, semicolon, end of line, you want to go next line, right? In MATLAB, semicolon, that means end of line, don't print anything. I think it does the same thing in Julia. Semicolon, you suppress the printing. But the best way to learn and memorize is just try it, see how it goes. Once you use the language, you get used to it. So these are syntax. They're not semantics. Once you understand the semantics, it's usually easy to play with the language and then learn a new syntax. So let's talk about a vector. A vector is a finite ordered list of numbers or variables. So there is an end to it. It's finite. It cannot be infinitely long, right? So there is a specific size for that vector, and that is always what we mean when we say vector. Now we have two options. A row vector has one row and multiple columns. If I call this one row, and then I have 1, 2, and 3 columns here. So V is a 3 vector, is a row 3 vector. 3 because it has 3 elements or entries. And it's a row vector. We can obviously try the other way. We can have a column vector. Now we have multiple rows and 1 column. So when you say row vector, the term that you use is unique. Row vector has only 1 row. Column vector has only 1 column. And you have many rows for a column vector. So the term that you say, that's the unique one. Okay? But it's easier to think about a column as a column, right? That's easy to remember. Now again, the entries are the same. It's just we can arrange it in a row and a column. It will become very important when we want to do matrix and vector multiplication later. There's a question that can you write an array like this? This is more of a lab question. 8.1 pi out of space. And then you close it somehow. Here or the next line. There should not be any problem. In MATLAB, you can do it. I think you can do it in Julia too. You can enter and then go next line. That makes perfect sense. So some people tried it. You can. I'm going to ask row or column. What do you think? You think if you do this, you get a row vector or column vector in Julia? Row, because we didn't use semicolon. But maybe inter is understood as next line. Nobody's answering. Column? Oh, no, that's a question. Owen, you did it. Tell us. Column. Owen did it, and it's in the column. So it's not row. Now, there is no right and wrong, right? It could be that you build a language to understand it as a row vector. So don't feel too bad about it. So how about if we have n vector, right? It's usually not the case that in a general context we want to specify a particular number of points. If we want to make a general statement, maybe we want to leave the actual size out, and n can be any, right, natural number. 1, 2, right? So the n vector has, a column n vector has n entries. These individual terms of the vector called element or entry. So that should not be surprising. We can do the same thing for a row vector. Okay? Now, n, for example, what if n is 10,000? Can you come up with or even better? Let's say I need to use calculator because I want to make a very specific example. All right. What if n, for the example I want to give you is 307,200 entries are in one vector. What example can be that? Yeah, it's just a real life example that we need to store this many numbers in one vector. That's not a vector you want to write down on a paper. You don't want to even look at it probably in the computer necessarily. You want to manipulate your data, but you don't want to maybe check some of it, but not really look at it. Now, you don't have to come up with this exact number. What's an example that we need so many numbers?
Population. So like if you're taking a survey of population.
Survey of population. Sure, yeah. We have a lot of people in the country.
If you're doing like autonomous driving, you have a lot of consensus, a lot of different information.
A car driving.
Yeah, like a car.
Yeah, if n is a time stamp of data, for example, you record, that goes on and on, right? These self-driving car companies, when they record a lot of data for their machine learning applications, they are collecting data continuously. So They usually have more data than they can actually use. Something easier. One image that I take with my camera. If you have an image, and it has 480 pixels here and 640 here, you get, so image is just an array of numbers. Let's just say it's a grayscale image, because if it's color, you have 3 arrays. One for red, one for green, one for blue. You will have this in your project, you will see. Project 1 or 2. So it's actually like this. It's a rectangular array, but I can make it flat. There's nothing wrong with that. I can just make the matrix, squeeze it in, make it flat, right? Cut this one and put it here, right? And so on. Just flatten the matrix. Now you get 300 or 7,200 pixels. Each pixel has an intensity for a grayscale image. Maybe the range of that is between 0 and 1, maybe 0 to 155, whatever is the intensity range of the color. And then you can visualize it in a computer. A lot of points. Now, this is not a HD image. Now, your camera today that you buy, and probably looking forward for the new iPhone or Pixel 6 or whatever you want to buy, that's going to be, I don't know, 8 megapixel? Bigger than that. 12? We lost the count. So that's even so much bigger than that. So one image you store so many numbers in the memory. And every image processing operation that you want to do is going to manipulate these numbers somehow. So we're talking about a really, really large scale operations to use linear algebra for a very, very simple task that you might imagine. I'm going to run a filter on my image to, I don't know, extract edge, put a bunny nose, or whatever you want to do, right? So it needs to process that image and numbers to do that. So it can be fun, so it doesn't have to be just a bunch of numbers. You can visualize it and do a lot of fun things with them. Oh, we had another population example in chat. Jesse said camera image. Population data will be interesting too, because you have an array, and then for every person, maybe you record a bunch of values for question. Now, the difference is that there might not be numbers, right? Maybe age is the number, maybe height. I don't think they asked about height, but what is an example of an answer in that array that is not a number?
Who you look for, so if you have names, you're going to have to keep track of like 3 or 4 different strings, maybe.
Names?
Names.
Yeah, they're named. Race, eye color. Yeah, so you might not be able to necessarily assign a number. Or can we? We can if, now I'm not saying they do it necessarily, we can if you say I'm going to call blue 1, I'm going to call brown 2. If you code it like that in a table for yourself and it's defined, and somehow you make sure the computer understands it, and you can recall it consistently, you can do that. In fact, that's available as a data structure, and it's called enumeration, I think, in languages like C, maybe. So sometimes you want to enumerate, but it's really annoying to call 1, 2, 3. You want to call it by text because that's easy to remember. You want to enumerate over different cases. So in programming, you might come across these cases, and that's handled usually using some data structures that defines the mapping. Okay, we are at a point we want to talk about the generalization of vectors. matrices are the generalization of vectors because we can just put two vectors next to each other and that's a matrix. We can put three vectors next to each other, that's a matrix. So this is a 3 by 2 matrix. It means that we have 3 rows here and 2 columns. Or you can think about it that I am just putting two column 3 vector, right, next to each other in a row. In a block-wise sense, if each vector now is a block, I'm just putting blocks in a row. That creates a, you should exactly think about it like a Lego, right? You're just putting these blocks next to each other, and a block can be a number or can be a vector. Now you have a matrix. So a matrix always has more than one column or one row, because a matrix with one column or one row is a vector. Just like a matrix with one column and one row is a scalar. A vector with one column and one row is a scalar. So we use the language that is the most specific to that. You can call a scalar matrix, but that's unnecessarily vague because, well, you just mean one number, scalar. It's so much easier to communicate like that. So we tend to use the name that is more specific.
What's the difference between arrays and vectors?
The question is, what is the difference between arrays and vectors? So arrays are more general. A vector is an array of number that is listed in one row or one column. You can have an array of text objects, right? An array of images, maybe. So it's a more general concept, but you could use it interchangeably too. You could just call the vector an array. Yeah.
Okay. I was going to ask if matrices and what makes that. I mean, arrays are a way to conceptualize matrices.
It's very difficult to hear. Please repeat your question.
I was going to ask if arrays were a way to conceptualize matrices in this particular.
Yeah. Yes. The question is, can we use arrays to conceptualize matrices? And yes, that's exactly what we do, right?
Is that like in the same sense as the vectors? Are matrices only numbers? Like it's a number type of array, and it says like a vector is a number type of array?
Yes, yes.
So you can't have like a matrix of like strings?
You can have a matrix of strings, but we don't know what to do with it, and we usually call it an array of strings. So in the linear algebra sense, we don't know what to do with it, unless you convert those texts to numbers again. So matrix and vectors, when we say we deal with numbers. Yes?
Aren't arrays just strictly numbers? So by definition, like in the slide, it was saying that it's scalar is arranged into a list, whereas a vector is a finite ordered list of numbers or variables. I think variables can possibly be like strings.
So let me draw this. It becomes a source of confusion. I'm going to say this is the space of arrays, right? In a subset of this space, we have matrices. Now, within that, we have vectors. So every matrix is an array, but not every array is a matrix. So every vector is a matrix, but not every matrix is an array. So it works one way, right? Because one is the superset of the other one. Matrices contains vectors. You could say this about any other concepts too.
So, like, what are like the properties that
So an array is a matrix, right, if all the integers are numbers, right?
Yeah, but like, what is like differentiating between like arrays that are vectors versus arrays that are not vectors?
It's a good question. I'm just going to complete this. This is maybe a scalar. Okay. So the question is, how can we say an array is a vector or is a matrix?
Or matrix.
Yeah. Now, a vector like A here, for example, cannot be a vector because it has three rows and 2 columns. But V here is a vector because it has 3 columns and 3 rows and 1 column. So you need the number for the rows or columns. One of them should be 1. Then it's a vector. What if both of them are 1? Well, then it's a scalar because it's just a number, right? You could say 3, 2, 1. Now, this is also a vector because the number of rows is 1. So one of them must be 1, then it's a vector. If both are 1, it's a scalar. If none of them is 1 and still you get a nice set of numbers, that's a matrix. You could generalize it that what if it's not a number, you could have an array of strings and text. We don't deal with that in linear algebra. In a programming language, you could do that. That's called an array or list. In Python, you got a list of lists, something like that. So you could give it different names. So hopefully this picture cleared the hierarchy of terminology that we use. What was the question? Well, hopefully the answer was clear. But we were talking about arrays, matrices, vectors, and numbers. And what makes something an object a scalar, a vector, a matrix, or an array. Now we want to go ahead and define A in Julia. So we learned how to define vectors in rows, vectors in columns. The obvious idea is that, well, let's combine them. Maybe we can make a matrix. And that's how exactly it works. You make the first row, use comma or semicolon here to go to the next line. Then type the next row, 3 and 4, use semicolon to go to the next line, and type 5 and 6. And then by doing that, you create a 3 by 2 matrix. Now in Julia, it's telling you this is an array because the computer considers it as an array, but it's telling you that it's an array of integer. So it is an array of numbers, so it's a matrix. Yeah? Yeah, you can do that. It shouldn't be any problem. It comes down to, I guess, personal taste and choice. Like some people use a space, some people use tab. It is hard to convince somebody who prefers one of them that the other one is better. It's probably impossible. Okay. Well, what about 2 by 3? We can do that. That's not a problem. This is a 2 by 3 matrix. Why this is a 2 by 3 matrix? Exactly. It has 2 rows. You can write 2 by 3. First, we write the number of rows times the number of columns. So it has 2 rows, 3 columns. So we type the first row, use a semicolon, go to the next line, type the second row. Now, can we type this column-wise? It gets weird. I don't think we can. So by construct, it makes sense to type the first row and then go to the next line, because I guess that's just, because then when you go to the next line, you can't go back to the previous line when you're typing the array, the way it's defined, right? Unless you build each column and later in more advanced exercises you will do it. Maybe you have the columns and you want to stack them, then you might be able to do it. So always think about, I'm building the first row, and then I'm going to build the second row, and then I'm going to build the third row, and so on. So we call this a rectangular matrix. Guess what? Because it looks like a rectangle. Aren't you bored? All the names are obvious. There is no need for creativity. Just call things the way they are. That's the best way to do it. What about a rectangular matrix? What is the condition? What about a square matrix? Sorry, this is a rectangular matrix. Now it has n rows, m columns. When we want to write it in general, it's very common to write it like this. So I have all the entries with their indices. Remember, the first one was the row index. Terrible. Then you say A, say I, J. Row, column. That means that you go here, you find column I, and then you find column J, for example, right? Whatever that number is, you cross another line, the intersection of that will give you that entry IJ. That's how you can find it, okay? So we have an n by m, n rows, m columns in general to form a rectangular matrix, just like the image I described. It wasn't a square, it was 640 by 480, something like that. Which is, by the way, typical image size that we process on the robot. Even if the camera is HD, the computer can't handle that. That's just too much. We usually downsize the image so we can run it in real time. Okay, how can we make this matrix a square matrix?
When n equals m.
Perfect. This is a very solid way to say it, because we can formally say when n is equal m, there's only one way to interpret this, right? They have the same number of rows as the same number of columns. Therefore, it must be a square matrix. And that's exactly what it is. Then you don't need to use m. Or you could use m instead of n. You use one letter because they're equal. A mini quiz for you. How can I locate this element? I give you A. I tell you find, using this indexing principle, find this entry. What do?
You go down to the fourth row and then over to the fifth column.
Right. You go fourth row and fifth column and find it. Now, this might sound simple. Might not. It's not obvious. You need to get used to the language. But when we arrange systems in linear matrix form, it's very important.
Is that built into the language, or is that just the notation for this class?
It's very standard. I think throughout your career, you will see just this indexing.
Because I would imagine it would follow something like a spreadsheet, where you have the it's usually lettered rows on the top and numbered, or lettered columns on the top and numbered rows.
Oh, so you're talking that you open Google Sheet or Microsoft Excel and it says A, B, C, say 1, 2.
Yeah.
Yeah.
So usually if you want to get to B2, it would be B, which is the column first, and then 2, which is the row. So I'm confused when you say that it's
Okay.
row column.
So let's see if I am not prepared to answer this question. Let's see if we can formulate an answer. I think first thing to realize is that Microsoft Excel, do you write it like this?
EXCEL, but that's difficult.
Does not equal linear algebra. In case you didn't know that. Different companies. These are poor mathematicians, these are rich people in Seattle. The second reason is that what if you want to, now you have, what if you have Z and then you have AA? What do you do after that? Triple A, quadruple A. Well, you could just call this 1, 2, 3. Well, this is really C1, C2. This is R1, R2. I mean, it could be like that. You open it as C1, C2, C3. Right? So that's a choice for designing that GUI, graphical user interface, by programmer.
I'm not arguing letters versus numbers. I'm arguing why put the row first. I guess it's
Oh, why put the row first? We don't have to do that. But it's very common in linear algebra books to do that. Okay. I misunderstood the question. The question was why not 5, 4, right? Yeah. Just a different convention. Yeah. Okay, so we talked about that. What is the diagonal of a matrix? The diagonal of a matrix is all the term that you can find on the diagonal of this square matrix. You can use this notation. Diagonal of A means diagonal of A. You can arrange the terms in diagonal into a row vector or a column vector. It doesn't matter. That's the diagonal. This means that you can go back and forth. When you know this is the diagonal, that means they are arranged on the entries that you have the same number for row and column. A, 1, 1, 2, 2, 3, 3, n. So we call this a diagonal, the diagonal of a matrix. Sometimes you might see it's called the main diagonal. It's shorter to say it's just diagonal. How about the other elements? For the lack of creativity that we have, we call them off diagonal, just not on the diagonal. Okay? So we can classify a matrix to 2 sets of numbers, the ones that are on the diagonal and the ones that are not. The ones that are not on the diagonal, we call them off diagonal. So all that background to be here. We want to use this notation, understand it. What does it mean to write AX equals B? This is important enough to put it on the cover of the linear algebra book or some engineering books. Yeah, you have a question?
Yeah, well, I was going to guess.
I'm going to tell you. What was your guess?
Well, we were talking, maybe it was in the book, but it was like matrix multiplied by a column is going to give you a bunch of different.
Right, but we are not there, so I might distract the class if I say that.
Sure.
But that's where we're going next time. So A is an n by n matrix. X is a column n vector, and B is another column n vector. Now, the question is, we learned all that matrix and vector stuff. First lecture, we learned about these lines of equations we use. And can we arrange them into matrix form? By looking at this, I want to arrange it in a matrix form. Well, it turns out we can, right? And the reason we can, because we ordered them, we keep x1 here, x2, x1, x2, and we numbered these nicely, right? So it already looks like we can arrange it in a matrix. And maybe x1 and x2 and b1 and b2 into column vector. Why? We'll learn later why, because that's how it makes sense if we want to do some operation like multiplication with matrices and vectors. That's a logical way to do it. So we can. So you don't need to use plus and other stuff. You can just put the coefficients in a matrix. Call it A, call this X, call this B. So when we say A, X equals B, we're actually talking about a linear system of equations. Now, it was very painful to talk about a general number of variables and lines. Now that we have access to matrices, we can construct any number of equations. At least we can store it like this in Julia, right? We don't know how to solve it yet, but we can store it in a computer easily like this. Okay. You have a question? You have a question? No? Okay. So that's the motivation for doing that. In the general case, can be hundreds of thousands. We have many lines of equations and many variables. With the same principle, we number them, rows, columns, and our variables. You probably want to take a moment and think about it, and maybe if it's confusing, post it on Piazza why we can do this, but based on this indexing, right? You put A1, 1 in the first row and first column, then x1, x2, xn.
Does this only work if you have the same amount of matrices and variables?
That's a very good question. You can still build a system. There will be some problems in terms of solving it, but we're also not solving it. So this is the standard case. Same number of equations, same number of variables, right? You will see it in the example that is for project 3. We actually don't have enough number of equations. So we will have to use some other tricks to solve the problem. This is the ideal case, standard case. It's often that in practice we either have more or less.
And we'll go over why x1, x2, that matrix is in a column.
Yeah, we will cover that when we talk about matrix multiplication. We'll tell you that these two must be the same. Otherwise, it's just not defined. But that's for the future lectures. Notation. This colon equality sign means define. In math, when you see this, that means that it's not that I can derive B to be this vector. I'm just defining it to be, right? It's not coming from anywhere. It's not a fact. I am defining B to be this list of numbers. And you only use it the first time because once it's defined, then you can reuse it. Some people use a triangle and equality sign. This also means define. It's a definition. You can use the other way as well. You can put if the letter is the other side, you can do this. So the colon goes to the side that you're defining the variable. But what you see on this slide is the common way of doing it. Examples. We want to express this system of linear equations into the matrix form. Maybe you want to try. Take 10 seconds. See if you can do it. So first of all, what is the problem here as you're doing it? It's the same thing. It's a practice, but it has a trick into it as well.
Upon first introduction, it seems like we're missing variables.
Missing variables. So we have x1, x2, x3. Well, putting these into x, it's not a problem. Same for b, right? 4, 2, minus 5. That's the easy part. For the matrix part, it's a little tricky because I don't see x3 in the first line. And I don't see x2 in the last line. Generally speaking, it's not a problem if you're solving it on the paper, but you cannot leave a gap in a matrix. You need to fill in all the entries. So the coefficient for the missing variables are zeros. You just add zeros. So this is 0 times x3, 0 x2. And by the way, there is really no need to be in order, right? x1, x2, x3. As long as you have the indexing, you can always get, but of course it's more painful to look at it and arrange it into a matrix. But that's not what we do eventually. It's not that our large system of equations on the paper, now somebody has to code it. It is already in a computer usually. It's from data. So missing variables, we add those and we get 0, 0. Now it's just the same as before. It should be straightforward. First one, we get 1, right? 5, 1, 5, 0. We get 3. This is a mistake. Was it minus 1 or 2? So this should be minus 1, right? 7, 7, minus 1, 0, 0, 2, 2. It's not much thinking. It's just, you just transfer them into a matrix once they are organized. And you can define the matrix A and vector B in Julia. Why not defining X?
Because you can't have a variable that is empty. So like, I guess if you were making the matrix with X, you would have like X1, but it has no value in it.
Exactly. Because the X is the variable we want to solve for later. We don't know its value. It's something that we want to find out about it. So we don't know. I mean, of course, we can define this a symbolic way. There are ways to do it in computer, but that's not useful here because that's what we want to solve based on A and B. That's correct. practice problem for you. We'll come back to it if we have time. But this is the first problem. You can put it into a matrix. Again, I can't emphasize more that this is really, really important, because ultimately everything will come into this form and then we solve it. If you find it a little confusing, practice. Let's talk outside of the lecture, make sure you understand. If you find it easy, that's good, because later we'll give you more challenging stuff. Wait until LU factorization. You are writing it, or you're solving it? Can I go to the next slide? Okay. Another problem. We'll come back to it if we have time. Determinant. An operational approach to talk about a determinant is to think about it as a function that eats a matrix, square matrix, and gives you a unique number. Meaning, if two matrices are different, the numbers will be different, right? Now, of course, it is possible to get the same number for different matrices, but generally speaking, it gives you a unique number. So so it's a continuous function. You give a matrix, if you change your matrix a little bit, that one number that you get from the determinant will change a little bit. A little change in the matrix, a little change in the determinant value. That, you haven't learned that formally, but that somehow is the notion of continuity. Changes in one side will lead to, small changes in one side lead to small changes in the other side.
When you say a square matrix, do you mean strictly a 2 by 2 matrix, or any
n by n matrix? But square matrix. The determinant is not defined for a rectangular matrix. The determinant of a 1 by 1 matrix is, not surprisingly, itself, because that's what it is, because we're not going to teach you crazy formulas of the determinant yet, although I'm going to show you for 2D and 3D. But a scalar, it reduces to just the same scalar value. There's nothing else you can do. For a 2 by 2 matrix, you might have seen this formula, or might be first time you're seeing it. It's very handy and easy. If it's just a 2 by 2 matrix, it's the product of the diagonal minus the product of the off diagonal. Now, I posted something on Piazza. This corresponds to the area that you can form with these vectors. Now, that's no trivial concept. It's a very, very advanced concept, because you need to understand what do you mean, these vectors, having a directions and forming that area, right? We get there later when we talk about vector spaces. That's like far away right now. So it's an advanced topic. But it's nice to know that it has geometric meaning. It's not completely abstract, although most of the time it's taught in an abstract way, unfortunately. So A times D minus B times C. Why do we need this? And different notations. This 2 lines. This is a standard way of showing the determinant. When you take the matrix, just put 2 lines on the sides instead of the bracket. That means determinant. or you can type it like this. Just different ways to show the determinant. And you have this crazy formula for the 3 by 3. Once upon a time, maybe I memorized it, but it's been a long time. I cannot write this on my own. So you don't have to memorize any of this. But there is a nice formula. And you can generalize it to any dimension, but now you can imagine that it's immediately becoming more and more painful, right? But there is a principle to it, and that can be turned into algorithm and coded, and then voila, you have linear algebra library. And so what you do, you don't memorize the formula. You go in Julia and say, using package, this is your package loader, add linear algebra, and then using linear algebra loads the library for you. Define your matrix A, and then get the determinant. That's all you need to do. Now, as we learn more later, you can come back and we can talk and make sense of it outside of lecture, right?
What is the use of the determinant?
Exactly. If there was no use, what is the use of the determinant? If there was no use, it would be useless to say these things, right? And I agree with you. There would be no point, except if you remember, we had 3 conditions for the solution of a linear system. Why does the determinant matter? Because the first one was that the solution is unique. The second one was there is no solution. The third one was that there's an infinity of solutions. Now, given how easily you can use computers to calculate the determinant these days, right? Given that now you learn how to put a linear system of equations to the matrix form, you just define your A matrix and take the determinant. If the determinant is not 0, you have a unique solution. Everything is perfectly fine. So it gives you a tool to quickly check if the system has a unique solution or not.
How does this determinant relate to like the b squared minus 4ac? The other one, like when you're solving a quadratic, I guess that's more of a quadratic. Like how does those relate at all? The quadratic determinant versus this?
The quadratic formula.
Like when you do the like b squared minus 4 times a times c, and then if that's
Oh, no, we're talking about linear. No. Now, somebody might come and say, no, they're actually related if you do this, but I don't know. but as far as related to us, we're talking about linear equations. You do not need to think about those stuff. No need to relate them. So if the determinant is not 0, we have a unique solution. That's a very easy way to check. Otherwise, we cannot know that by just looking at the equations. Yeah?
So you said the determinant only works for square matrices. What do you do if you have a rectangular matrix?
That's a very good question, but it's very advanced.
Would you just always try to have a square matrix?
So I can just say for now that once we learn more, I can formalize it for you. But if you have more equations than the number of variables, we can convert it into a square system. By having extra information is fine. Having less, we can do that, but still we need to add extra constraints somehow. That's in project 3. In model predictive control, Jesse will teach you that. That's the idea behind it. But yeah, in general, if you want to actually solve it, it needs to end up being in some form of rectangular system. Although we will teach you QR factorization in future lectures, you can bypass some of the steps, directly work on the rectangular matrix. You can factorize it. That's a more advanced topic. So now if the determinant is 0, that's the sign that there's either no solution or there are infinite possible solutions. We don't know which, but both cases are bad. Now, practice problem. There's a problem, form A, and calculate the determinant. Try this because you need to follow those steps of loading, adding the package and loading it. You should try it once, right? First time, there might be a problem. See if you can fix that, right? There's no problem if you try it on Illumitex, but if there is, right? You will never get to this line. Okay, put this problem into the matrix form and tell us, now you can solve these and post it on Piazza too, these practice problems. And tell us if there is a unique solution or not. And with what you learned today, you can go ahead and form the matrix form, calculate the determinant in Julia. If it's not 0, then we know that there's a unique solution. Another problem, you have the slides. I can go back later for you to write it. So we covered everything we want today. I can go back and we have time. I can go back if you want and solve one of those problems to put in matrices. Because I think the recording continues until 2:50. But next time we want to talk about triangular systems. And very important topic of forward and backward or back substitution. These are in chapter 3. Once we convert this problem into triangular systems and learn forward and back substitution, that's where we can solve for x. In general, when we look at the system, there's not much structure to know what to do. These are the ways to add more structures to the problem. Then using the structure, we know what to do. That gives us a set of rules that every time works. So we can solve it using just following those rules. Now I have to tell these rectangular systems and some of this stuff to my graduate students too when I teach a grad course for robotics. I wish everybody knew Rob 101. Sometimes they forget, sometimes they never learn. Because they come from different backgrounds and degrees. Very important, because that's what we use to solve many problems that later we talk in the course.
What's the best way to access Julia?
The best way to access Julia, maybe instead of writing that, I'll talk about this. So if you go to Canvas, Illumidesk, right? Now, you can install Julia on your local computer. You can Google it, go to the website, install. This is on Windows. If you use Mac, you can do it. If you use Linux, you can do it. That's not a problem. You can use it locally. But to not burdening you with loads of stuff, and you can focus on learning, we're using a web-based interface. So Illumidesk is a company that provides that for many things, including Julia. So we can run. Now we will see a different, I think, view because I have the instructor privilege. But for the most part, it should be similar. You go to Illumidesk, start your server, then you should see your files. You can start a Jupyter notebook. Originally these were Python notebooks, but Julia adopted that because it was very useful and popular. That's why the format is IPython. But this is, I think I should go to here. So you could run it locally, or you could just create a new file here and start typing. Start a block of code, right? I go here, you can add here a new block of code, or you can add a block of text. This text that you see is called, I think markdown, is it markup or markdown? I forgot. I think it's a markdown language. So markdown language is what you see also in GitHub and some other interfaces. It's a very nice way to type text, also use equations and add figures. Super easy to work with. So the actual code is like this. So you can type, but when you use dash and nested dash, it knows that you mean lists. When you add these hash, then you use more. It creates sections, subsections. So that's how we run it.
It says linear algebra is not a valid package name.
Your package is not available.
No, I guess.
Worked for me. Did you put a space in between or no?
Yes.
Don't put space.
Really?
There you go. Now, it turns out that you shouldn't put a space. That should have been correct on my slides, right? Because
Yeah, it was right on the side.
Oh, I added a space in the notes.
so the question was that somebody tried on Illumidesk to load linear algebra package. That's exactly why I wanted to try, and it didn't work. Because you shouldn't put space here.
Yeah, so the determinant of problem 1, I got it.
I'm going to keep the answer secret.
Do I keep the answer secret or do I?
Yeah, post it on Piazza.
Post it on Piazza.
If you want to get credit, post it on Piazza.
Oh, okay.
Then we will like your post. All right, so that's it for today. Next time, on Monday, I'll see you, and we'll talk about triangular systems of equations, forward and back substitution. See you next time.